Hello level 3s. So in the last video we looked at why is the energy of the nucleon that's bound, the nucleons rather, that are bound inside the nucleus, why is that less than the energy of a free nucleon? And the reason is that the rest mass of the nucleus will always be less than the total mass of its parts, so that number of protons and the number of neutrons together. Now that difference is called the mass deficit. Okay, so we're going to look at what binding energy is. We're going to interpret graphs of binding energy per nucleon. We're going to look at fission and fusion, and then calculations involving mass deficit and energy release. So what I've just said, the total mass of a stable nucleus is always less than the sum of its constituent parts, which are nucleons, or otherwise known as protons and neutrons. So if we had a look at this nucleus on the left, it might be lithium nucleus because it's got 3 protons and 4 neutrons. And so with some binding energy, in other words, if energy is added to this bound nucleus, then the particles will be freed. Okay, the subatomic particles. So if we go the other way, then energy will be released in order to form the nucleus. Got it? Hope so. Okay, let's have a look at this example. You can write this one down. So on the left of the diagram, you can see we've got an alpha particle, and you all know that's a helium nucleus. And if we looked on the right, that is if it was unbounded or unbonded, I guess, not in a nucleus state. So if we looked at a proton and then 2 neutrons, and we looked at their rest masses, and we added up all those rest masses, the sum of the rest masses, we would find this number. The sum of the rest mass of the alpha particle is this number on the left. If you compare those 2 rest masses, which one is bigger? The rest mass of the individual particles, the sum of the individual particles. And so there's an extra mass on the right of 0.03035 atomic mass units. So that extra mass is what we're going to put into our equation, E equals mc squared. All right? So just to make sure you understand that, there's more mass if we add up individual particles, and the mass of the nucleus includes this binding energy of the nucleus. So this reduction in mass between the left and the right, rather the right and the left, is called the mass deficit. So the binding energy is the amount of energy which must be supplied in order to make up the mass deficit. In other words, to separate the nucleus into individual nucleons. Possibly, if you'd like to think of it as playing snooker, and if you need to break up that initial triangle of all the snooker balls, you need to provide energy, and that is provided by something from the outside, like a cue or a different snooker ball that is hit into that triangle. So you have to, the binding energy is that amount of energy supplied, given to the nucleus in order to separate it into its individual nucleons or protons and neutrons. So the energy has gone into another kind of energy, such as radiation or kinetic energy, when this formation occurred, in other words, when the nucleus was formed. So the mass or energy difference is what we refer to as the total binding energy of the nucleus. So the amount of energy each nucleon has can change. One of the most important things. So if a nucleon is pulled out of the nucleus, work has to be done so the energy of the nucleon increases. So if we compare this to gravitational potential energy, and you have a box, let's say, lying on the floor, and you lift that box up, right? What have you given the box? You've given it more potential energy. So similarly, to break the nucleus into separate nucleons, the mass deficit must be restored by adding more energy, right? So you're adding more energy to the nucleus, and that energy contributes to its mass. Remember, so we're looking now at level 3, we're looking at mass and energy conservation. It's no longer just mass conservation or energy conservation, it's now mass energy. So energy can become mass and mass can become energy. So according to Einstein's E equals mc squared, we know we can relate those two things. I've just put this in here, the electron volt. We've covered it in class, but pause the video at this point if you want to go through that again, because we're going to use it in the next question, the next example. So on page 208 is this question, and you can pause the video here after the explanation if you want to go through it in your textbook. That would be a good idea. But what you need to look at here is we're going to find the binding energy of a tritium nucleus in joules and in electron volts. Right? So we get given the rest masses of, oops, the arrow's in the wrong place, of protons, neutrons, and the tritium nucleus. Okay, so that's that last one there. So the mass deficit when forming tritium, so you've got to subtract the two masses, then using E equals mc squared to find the binding energy in joules, and then we're going to convert that into electron volts. So let's just go over that one more time. What we do is we've got a proton, one proton, two neutrons, right? So total that they have that mass, and if they were all together already, so if they're individual particles, let me just confirm, then their masses together are these top two. If, however, you have mass of all the particles together bonded or bound into a nucleus, then this is the mass of all the particles. So taking a look on page 208, and you can see there how the example's been done. Now, in order to compare different nuclei, we're going to have to look at the binding energy per nucleon. So it's like an average for all of the nucleon particles. We're going to find the binding energy per nucleon. So the larger the nucleus is, the bigger the total amount of binding energy. But so you are absolutely certain what this is all about. And what we're needing to do is compare a large nucleus to a small nucleus. What is their binding energy like for the nucleon? And so the only way to do that is to work out an average, so per nucleon. So we're going to use that information. And this graph has been plotted using that information for each type of element. So you can see here that we've got things like some of the helium and hydrogen isotopes up to here, lithium, again helium, that would be the stable helium, carbon, oxygen, neon, magnesium. And so as you move down on that periodic table, so you're moving up on this binding energy per nucleon graph. So the binding energy per nucleon becomes larger until you reach a point here at the top of the curve, if I can find my mouse, where the largest binding energy per nucleon is for iron. Okay, up there. And if you move across to the right, you can see that the graph dips. So as the particles get larger and larger and larger, so their binding energy per nucleon decreases, right? So the more binding energy per nucleon that is required, the more stable the nucleus will be. So which is the most stable nucleus? Iron. So paste that one into your notes. I'll give it to you in class. Then looking at the mass per nucleon graph, I will give you this graph as well in class to paste in. So if you look at this graph again, you can see that iron is the most stable element. Its nucleus has the greatest binding energy per nucleon, and we saw that on the previous graph, which means it needs the most energy to release a nucleon from an iron nucleus than any other element. This video is becoming a bit long now, so I'll rush off to finish this graph quickly. This shows that the nuclei whose nucleons have the least energy, right, and therefore the greatest binding energy, also have the least mass per nucleon. So this is the least mass per nucleon. So again, that's iron for you over there. So a large binding energy per nucleon means that the nucleons themselves have the least amount of energy. So as mass includes energy, remember, the nucleon mass of the nuclei that have a large binding energy per nucleon will be less than the nucleon mass of nuclei that have a lower binding energy per nucleon. So did you get that? We'll go over this one in class one more time. So just to rephrase, these are the least tightly bound, and these ones are the most tightly bound at the bottom of the curve. These are also becoming less tightly bound to the right and higher up for the bigger isotopes. All right, so we'll stop there and we'll carry on in class.